Okay, in this video we're going to talk about a concept called resonance structures, and it's going to be a little bit of a weird topic. This is the idea of delocalized electrons, or delocalized bonding is probably the easiest way to phrase it. So the problem with Lewis structures is that we draw everything as lines or dots, okay? And it tells you exactly where those electrons live. The problem is electrons are particles that are moving in near the speed of light. They essentially are like a cloud of electron density, and they can move around and form new shapes. They can move wherever they want. Lewis structures tricks you into the idea that they live at one spot. They technically can move wherever they need to. So this is the idea of what happens when electrons move around and don't stick where you put them. The idea is if a molecule has resonance structures, which we're going to figure out how that works, more resonance structures, or resonance contributors, some books call it, more resonance structures equals more stability. Because essentially it's usually a matter of like moving a charge around. Having localized charges is inherently unstable. Okay. Anytime you have resonance structures, they should have the same distribution of atoms and formal charges. None of this will make sense until I do some examples, but I'm trying to put it all in writing. Okay. So let's just look at an example. Okay. So an example we did in the last video was nitrate. And what we did was we got to the point where we had this. So if you don't remember how we got to this point, please go look at the previous video. But we got to the point where we needed to make a double bond on this nitrogen. And we said, oh, we have 3 oxygens. It doesn't matter which one you choose. And technically I didn't lie to you. But what I will tell you is that because we have 3 choices, all 3 possible options occur. Those are the 3 resonance structures. So because we have 3 equivalent choices, we actually technically end up with 3 structures. Okay. So one option is to have the double bond on the left and have the single bonds on the top and the right. Another option, and this is how you this is the arrow we use to distinguish between different resonance structures. The other option is to have the double bond at the top. Okay. And the other option is to have it on the right. So we have 3 different structures. Okay. More resonance structures equals more stability. So resonance structures are actually a good thing as far as this stuff is concerned. On the last video, we also looked at how to get the formal charges. I'm only going to worry about the things that have charges. So the nitrogen is +1, this is -1, -1. Over here, this is -1, +1, -1. This is -1, +1, -1. Okay. So the idea is these are the possible extreme options of what is available for this molecule. Okay. And so these negative charges are actually getting shuffled around across all of the oxygens. The nitrogen's always positive, but the oxygens are not. They're only negative like 2 out of the 3 structures. So what that means for us is this negative charge is not being localized. It is unstable to have electrons have negative charges or positive charges in one spot. If you can move it around, it actually makes a more stable molecule. Okay, so that's what's happening here, is this negative charge is kind of getting shuffled around. If I ask you on a quiz or exam for resonance structures, this is what I want out of you. These are all the 3 possible options, just draw all 3. I will tell you that in the real world, none of this is correct. What you technically have is the average of all of these. It doesn't jump back and forth between each of these 3 structures. It exists in between all 3. Okay? So the correct answer is a little weird to draw. I'm going to do my best. They all have at least that many electrons on it. So what happens is, if we look at just the left bond, the left oxygen, it has a negative charge 2 out of the 3 times, and it has a double bond 1 out of the 3 times. So what we end up with is something in between a single bond and a double bond. And the same is true for like the top one. Single bond, double bond, single bond. So we end up with like a 1 1/3 bond. It's a little, okay, it's really, really weird. Okay, see if I can find a way to label this. So it's not a single bond, it's not a double bond, it's like 1 1/3 bonds. And the charges, this is +1 all the time, but if we look at, say, the left oxygen, here it's 0, here it's -1, here it's -1. So 2 out of the 3 times it's -1. So this technically has a 2/3 charge, or -2/3 charge, -2/3. And so I do not ever need you to draw it like this, because this isn't super clear. But what I will tell you is, if I ever ask you for resonance structures, or if you ever have to do this in like organic chemistry, these are the resonance structures. This is what we would be asking for. What I need you to be able to do is visualize that it is the average of all of those in terms of distribution of charges, distribution of bonds. This is kind of weird abstract stuff. Okay, let's try a couple more examples and see how this goes. Okay, see if I have room down here. One of the other examples in the previous video was acetate. Okay, and we had this structure. And we had the option to put 2 double bonds. Or we needed a double bond and we had 2 choices. Kind of like up here, we needed a double bond and we had 3 choices. So because we have more than one choice, we have 2 possible options, we end up with 2 resonance structures. Okay, so one option is to have a double bond at the top and a single bond on the right. The other option is to have the opposite. Oops. And kind of like we saw up here, we're going to look at the distribution of double bonds and charges here. The only charge on here is that the single bonded oxygen has a -1 charge. So if I asked for the resonance structures of acetate, this is what it would be. Okay. What I need you to be able to visualize, I do not need you to draw it, I just need you to be able to think through it, is that this is really what the molecule looks like. You have somewhere between 1 and 2 bonds, a single bond and a double bond on each of these. And so what you end up with is these are both 1.5 bonds. So in between a single bond and a double bond. And on average, each of these, so on this, if we look at this top oxygen, it has a 0 charge here and a -1 charge here. On average, has a charge of -1/2. So it's a way to distribute the negative charge out more to make this more stable. Okay? Stuff's a little weird. It's not impossible, but it's definitely a little weird. Okay. Let's try maybe one more. Okay. So oxygen, the typical version of this is O2. That's what we're used to seeing. There's another option called O3. This is ozone for what it's worth. It forms a protective layer at the top of the atmosphere to keep ultraviolet light from, giving you skin cancer. It's also a toxic waste, not toxic waste, I guess, but toxic fumes that come out of a car. Okay, so if we were going to do this, we would say oxygen has 6 electrons times 3, that's 18. Yay! You'll note that we do not have a charge. This is not an ion. Okay, it's just a regular molecule. Okay, our choices of central atom are oxygen or oxygen or oxygen, so it's oxygen. Okay, great. We've used 4 of our 18. We're going to make sure the outer ones have what they need first. 2, 4, 6, 8, 10, 12, 14, 16. We have 2 electrons left. Step 3 says to place the remaining electrons on the central atom. Maybe that was step 4. I don't know. Yeah, that was step 4. Step 5 says to check for octets. This is happy, this is happy, this is not. So what we're going to do is we need to form a double bond. We have two choices, so we get two resonance structures. You're probably noticing a trend here. Oxygen is not the only thing that can have resonance structures, but it's a pretty common thing that does. Okay, so essentially we're going to have one option where there's a double bond on the left and a single bond on the right. The other resonance structure will have a double bond on the right and the single bond on the left. If we look at formal charges, this is 0. This is 6 minus 2 minus 3 is plus 1. And this is 6 minus 6 minus 1 is negative 1. And the same thing in reverse here. Okay. So, I didn't leave myself space to do this, but the average of these would be essentially, it's always going to have a lone pair in the middle. You're always going to have at least 2 lone pairs on each of the side ones. And we're essentially going to have like 1.5 bonds on each side. Okay. And the charges, if we look at the left oxygen, it's 0 and negative 1. This charge is essentially a negative 1/2, and it's the same thing on this side. And this middle one is always plus 1. So it still adds up to 0, but this distributes the negative charges better, which stabilizes the molecule. Okay. Resonance structures are a little weird. I will tell you that if you make it to like organic chemistry, I know when I used to teach the class, there was an entire chapter about reactions that only work because of resonance structures. So unfortunately, this stuff never goes away. It's pretty critically useful. Okay? All right, thank you.